Here we have the ratio of the infinite series, 3 to the n dividing by 5 to the n plus 1, and we want to show that it converges using the ratio test. So we want to use the ratio test to show that a series converges, then we have to show this. So we need to show that. So we have A sub n is this. And so B sub A sub n plus 1. So in the place of n, we put n plus 1. And then now we need this to find this ratio right here. And then we can simplify this a little bit first. This means 3 to the n plus 1 is 3 to the n times 3 to the first. So A sub n plus 1 is that, and then A sub n is this. And then we can simplify a little bit. The 3 to the n and the 3 to the n will drop out, and then what's left is just this one. So the 3 to the n drops out, and then this 3 to the n drops out, and then when there's nothing left here, we put a 1. And so this right here, this means that is the top and then times the reciprocal, the bottom. So dividing by 1 over 5 to the n plus 1 is the same as multiplying the reciprocal. So it'll be 5 to the n plus 1 dividing by 1. And then let's rewrite this as this. So that way we can take the limit a little bit easier. And then now we need to find the limit. And then 3 is a constant, so we can go ahead and move it to the front. And then we need to find the limit of this right here. Now, so let's find the limit of the 5 to the n plus 1 dividing by 5 to the n plus 1 plus 1. And so the corresponding continuous function is this. So instead of n, we have x. And then if we find the limit of this right here, then obviously we'll get infinity over infinity, because 5 is x approaches infinity, 5 to the x will approach infinity. And then as x approaches infinity, 5 to the x plus 1 also approaches infinity. So right here, then we can use L'Hopital's rule. And so what that means is that we can define the derivative, we can take define the limit, we can take the derivative of the top and the derivative of the bottom. And then recall the derivative of a constant, an exponential function like a to the x is be ln a times a to the x. And so here we want the derivative of 5 to the x. So the derivative of 5 to the x will be ln 5 times 5 to the x. And then we also need the derivative of 5 to the x plus 1. But 5 to the x plus 1 is the same as 5 to the x times 5 to the first. So this becomes 5 times 5 to the x. 5 to the first is just 5. And then, so here we get 5 times, so this is just the multiplication constant 5. And so we need to just do the derivative 5 to the x, but the derivative 5 to the x is this, is ln 5 times 5 to the x. And so now we can find the limit here. Once again, the L'Hopital's rule says that we can take the derivative of this and then take the derivative of that. The derivative of 5 to the x is just ln 5 times 5 to the x. The derivative of 1 is just 0. And then the bottom, the derivative for 5 to the x plus 1 is this. And then derivative of 1 is just 0. And so ln 5 will cancel out. 5 to the x will cancel out. And we get 1 over 5. So one more time, this part and this part will cancel out. And nothing left on the top, so we put a 1. And therefore this is less than 1. And so we have shown that the limit of the ratio, but this is the corresponding continuous function. And since here we're dealing with discrete function, so this means this. So back to our function right here. It means that this is 3 times the limit here will be 1/5. 1/5. And then this is equal to 3/5, which is less than 1. And the reason we couldn't use the L'Hopital's rule with n here because n is a discrete number. N is 1, 2, 3, 4, 5. N is not a continuous variable. And so to use L'Hopital's rule, we have to have continuous variable. So that's why we have to, instead of taking the derivative of this, we change it to the corresponding continuous function before we can do the derivative. But we end up with the same result. And so here we found that this limit right here, let's go ahead and copy this. The limit of the ratio a sub n plus 1 divided by a sub n is equal to 3/5, which is less than 1. And therefore, by Ratio's test, it says that if we can show that the limit of a sub n plus 1 divided by a sub n is equal to a real number less than 1, then we can say that the series converges absolutely. So we can say that this series right here converges absolutely. And so if a series converges absolutely, then it means that the series converges regularly.